All right, we'll get started in just a minute. I'm just going to write a couple of things up on the board to think about for a minute. All right, so what I want to start out with today is talking a little bit about some things related to your test. We're not going to go over the specific test questions, but some items related to a few common errors. Generally speaking, your tests were very good. Grades were same as usual about, which is good considering the fact that this is a kind of strange semester. But in any case, those grades, you'll see those are counted in your Canvas grades. Now, there are some slight adjustments made on a couple of questions here and there. So you might have seen one grade originally and a different grade now, but it would be at most like 1 point difference. In any case, one of the types of things that you were doing on this test was expressing net and total accumulation, or looking for expressions of them rather, using integrals. So if you remember, when you see an expression like this integral is understanding the pieces of it. This is understood as a rate function, the rate at which something's happening. So I have this rate used for an infinitesimal amount of time, or just distance along the horizontal axis if you want, where we're looking at summing up all of the change that occurs between independent values of 2 and 6. So in terms of things that we did earlier in the semester, this 3t squared, if I had that as a rate function, it would look like, something like this. So just imagining that 2 is here and 6 is there. I'd be looking at all the changes that occur due to using all the different rates between here and there, which at the smallest is 2 comma, 3 times 4, 12. So I'd be using that rate of 12 for the first infinitesimally small interval, and then a rate that's a little bit bigger than that, and a little bit bigger, and a little bit bigger, all the way up until, well, when we get to 6, and you don't need to work these out, generally speaking, when you're doing this, but just in terms of stuff we did earlier in the semester, let's see, 36 times 3 is 108. So by the end of this, our rate has increased all the way from 12 y's per x, whatever you want to call it in general, to 108 y's per x, whatever the meanings of this might be, whether it's miles per hour, people per day, people per square mile, foot per mile, elevation, that sort of thing. But in any case, what we did earlier in the semester is look at this, and if I was just concerned about, I'm going to write this at a scale that works better for doing this, if this is my exact rate function, which I know isn't really a straight line, but if this is my exact rate function, r sub f, then what we did when we were doing this manually is pick a few different rates and use them each for a little bit to get up through where we need. And we use these maybe for like 1 unit at a time instead of 0.00000001 unit at a time left to right. But this then just tells us the change that happens between independent variable values of 2 and 6. So of note, these are values of t in this question, or whatever, it could be x or whatever, the independent variable. They're things that would be replaced into this spot of the rate function, whatever letter I want to call it. Now, something like this would have all the same that we had from the rate, but there's this plus 5. Now the end of that comes in here. If I asked you what sort of accumulation would occur, I'd have accumulation starting at 2. So my net accumulation starts at 2. This is my reset at 0, and it starts increasing, slowly. And then for my approximate, it'd be this piecewise sort of function. But my exact maybe if I use smaller intervals, it maybe looks something more like this, but it starts from 0. Nothing's happened yet. If I just say, well, what happens starting at 2? Well, we start from a net position of 0, or whatever this might be, whether it's position, money, number of people, whatever it is, and it grows more and more quickly as we go on. So from this rate function, we have an accumulation function that follows. This is just net accumulation though. Clearly, if I just compare these two, the difference between them is 5. What that means in terms of this sort of thing, this gives us, instead of just net accumulation, or what happens only because of the rate, this expression here, its value is partially from the rate and partially from some place that we started before using this rate. So the difference in this, now this is a numerical value, right? So this is one number. It would give us that value there. It would tell us, actually what it would tell us is the change between those two. But if I talk about this, and so here, let me, instead of ending this at 6, I just ended it at 6 so I can draw these intervals ending someplace. Let me just draw this kind of in general how we did in most of the time. So instead of that, I'm just going to call this, ooh, I erased a whole level of stuff. But let me just say this goes up through x. And so then I can have a sub f of x looks like this. It starts at 2 and goes on through any general x. Exact accumulation would be something like this. Starts at 2 and goes on. At 6, it would have that particular value. The difference between 2 and 6 is what that previous statement would have calculated. This one here, let me do the same with this. If I'm talking about starting at 5 and then going onward, well, that just means that instead of being at 2, 0, I'm going to start at 2, 5. Notice this 2 is an independent variable value, whether it's t or x or whatever letter, wherever we're considering it in the process. This has to do with the independent variable. This number is added onto the result of all of this. So this is a dependent variable value of 5 that's added on. So if this is what a sub f of x looks like, this would be now maybe my f of x, total accumulation. So what happens due to the rate plus what happened, or what value we were at to start with before we started using this rate. So the difference isn't in the shape of the graph, it's in the position. It's just a vertical shift, knowing that initial information. But in any case, I just wanted to point out the difference between adding on an extra term or not. This is kind of like a MDX expression. So this tells us changes in y, dy equals MDX. This is just a whole bunch of different values of m, so it's a sum of a whole bunch of them. So this is a whole bunch of changes in y added together, but it gives us just a change, a net change in the dependent value between 2 and, well, anything else. So right now it's a function. This is like y initial plus MDX. So going back to where we were before, so I get actual individual y values out of this, not just net changes, whatever this might be. What is the overall elevation by 20 miles in from the coast? What is the total amount of money in the account after 2 years of working some job based on having some money to start with, or whatever it might be. But it has just one extra piece, which is an additional y value or dependent variable value that's tacked on to account for where we started at this value of the independent variable. So this all relates back to our fundamental theorem of calculus. I'm just going to abbreviate FTC, fundamental theorem of calculus, which you can interpret it a few different ways. But one of the ways that we interpret this is, so if I integrate any rate function, r sub f of x, or whatever I want to call this, from a to b, this tells me f of b minus f of a, the net change in a function f, whose rate function is here, I'm just using our notation that we've used in general. So the derivative with respect to x of f of x, we're calling this r sub f of x. So this fundamental theorem of calculus can be interpreted this way. Between two numbers, a and b, it's usually written in this order. But also, sometimes instead of having a b up there, you'll see an x in that position. So up through this general x, like what we were talking about here. And in that order, it's usually written in a different order. I'll use the same notation here, r sub f of x. Ooh, I want to write it here, and I realized I didn't write it last time, dx. So let me just start this one over here. If I need a dx there, and I'm doing a general version, I need different letters. R sub f of t dt from a to x. Instead of writing this as, which we could just strictly translate this, f of x minus f of a and have the exact same expression, usually how it's written instead is rearranged with this f of a over on the other side. So I have something that's a function definition, f of x equals f of a plus what happens after a up through any general x due to this rate and just dummy variable, temporary variable that we allow to vary from a up through x. So this is that y initial plus mdx structure, and this is like y final minus y initial gives us dy. So in any case, these both really say the same thing. It's just different ways of reorganizing it to think about different meanings that it might have. All right, so let's talk about, let's see, some other things from the test. I want to specifically look at, well, I'm going to pull up a homework question that you did, which was about water draining from a cone. And there's a similar setup on your test, but it asks you for a different piece of information. So we'll just kind of do the same sort of stuff with this other question. So the one in your homework, let me clear this out and reshare something new. Let's see. Not my desktop. I want the Google Chrome. All right, here's my iMath. So let's see, this was, oh, so while I'm on this page, take a look, I've got, this is homework that's due tonight. Most of it's stuff that I'm sure you already know how to do. It's just interpreting integral expressions. If you're rusty on that, I hope what we just did helped. We'll talk about a few more examples of just general antiderivatives, which is just undoing the process of finding a derivative or saying whose derivative do I have sitting in front of me. And we've done that on several different questions, but we'll go over some more tricky ones today. Let's see. As for this other assignment, this is a little bit trickier stuff that we're going to be talking about between today and Thursday related to other applications of the fundamental theorem of calculus. And this quiz covers the stuff that's on these two homework assignments. So just one last quiz. It's due on Sunday, 11:59 p.m. And then your final exam's on Tuesday. Somebody asked if you're going to be able to see your tests or your answers. No, those are not allowed to be seen. I can go over them with you, like go over questions that you have individually, but I'm not going to show you the tests. Those are, for test security purposes, not something you get. Let's see. Oh, I was looking for previous assignments. So it was this one, I believe, right before the exam, had your cone questions on it. Yep. Let's see, question number, conical water tank. So you had a very similar question to this on the test. So let me just talk about this one. So conical water tank, vertex down. We talked about this actually a little bit on, let's see, Tuesday last week, day before our last lecture before your test also. So we have a conical water tank, vertex down, radius is 12 feet at the top, 26 feet high. So that tells us overall relationship between the radius and the height throughout the cone, whether or not we're talking about the full cone. So whatever the, if we're talking about the whole cone, the radius at the top is 12 and the height overall is 26. Or in other words, the radius is about half the height. But that's true at any height. So if I have the water filled up to here, whatever this height of my water is, the radius at the surface of the water there is going to be in the same ratio. It's be a similar triangle if we take a slice through the cone and look at the surface of that slice. So in any case, whether it's a 12 to 26 ratio, it could reduce it to 6 to 13, which is actually what this asked about. But I'll just do it kind of more generally like was on your test. There's fewer computations. But let's see, one thing we need to know about this that was stated on your test, and I said you can look it up, is volume of a cone in general is given by 1/3 pi r squared h. But let's take a look at the things that are asked here. So if water flows into the tank at a rate of 10 cubic feet per minute, this is not the volume of the cone. This is the rate at which the volume is changing, right? So this is our dV dt. This is a volume measurement over time. So I'll call it dt using t for time generically as usual. We don't know how fast the depth of the water is increasing. So this was asking for how fast the height is changing. That's what we want to find out. We know a value for dV dt. We want to find dH dt at a particular point in time. So the question on your test was just more along the lines of how would you express dH dt at any point in time? So just asking for a formula as opposed to a computation. So the thing is that this formula involves R's and H's both. The general process for finding a related rates sort of answer, I have one rate, I want to find a different rate, is we need to relate the quantities first and then differentiate to relate their rates. Now this has an extra quantity in it that will be changing, but it's not independent of the height. It's not at some other random rate that has to be listed someplace, because when I know the height, I know the radius. No matter what the height is, the radius is going to be a little bit less than half of it. It's going to be 12/26 of it. We call it 6/13. So for any value of h, if I multiply by, I'll just write 12/26, so it's easier to see where this comes from. A little bit less than half of the height, that's what my radius is. So in this question here, if I wanted to rewrite this volume expression so that it's a function of just the other thing that we're looking for, so that when I find a derivative with respect to t, I'll have dV dt on the left and only dH dt's and not have some dR dt's also. There's no product rule that we need because, well, R can be expressed in terms of H. Maybe take a little bit of algebra to clean this up, but it'd be 1/3 pi and then 12/26 h gets squared and then times h. So this would be a formula V in terms of just h's, which is lovely numbers. On your test, there's just a half here, so much easier in that case. But I'd have what, 144 over, let's see, 676 times 3. And what I'm doing is just incorporating that with this. And also times pi. So I'm putting all the constants in the front, and then I've got h cubed. So this right-hand side would look like that. It's a messy coefficient. I don't really want to do 676 times 3, but you can certainly do it if it makes you happy. But here's a relationship between V and H. If I differentiate each side with respect to t, I'm going to have the same number. It's just a coefficient, and then times 3 from power rule, which is why I didn't want to bother with that 3. And then chain rule, since h is a function of t, just unstated, I'd have this for my overall expression that relates dH and dV, both derivatives with respect to t. So reduce that just for simplicity of looking at it. I'm sure something else reduces also. But if I wanted to express how fast or what's the value of dH/dt when the water's 13 feet deep, that's put in a value of h and put in our value of dV/dt. If I wanted to express it in general, just state a formula for how the height is changing, the rate of change of the depth of the water, that's just solve for dH/dt. So it'd be dV/dt over h squared and times the reciprocal of this fraction. So it'd just be, just rearranging this, which is what you needed to do on the test question that was similar to this one. All right, but in any case, once you get to here, whatever you need to do, whether it's plug in numbers or solve for one of the variables, it's just algebra at that point, although a little bit messy. Make sure you understand what is being asked for. All right, one other thing I wanted to talk about. Let me go back to the plain screen. Let's see, whiteboard, if it'll let me, maybe. There we go. So there was a question and that asked this more directly, and several that just kind of used the ideas where you're looking at graphs and interpreting what's happening. But let's say that I knew something like f prime of 7 is equal to 4. I want to know, what could you tell me about f in the area where x is 7? Well, if f prime of 7 is 4, this is a rate of change that's 4. So I don't know precisely what's going on, but I know that it is increasing, right? Because that's a positive derivative. So if I said like f prime of 3 is -2, that I know that in the graph of function f around x equals 3, it would be decreasing. Whether it's I'm looking at a graph and say this is a graph of f prime, and you can see these coordinate pairs 7, 4 and 3, -2. You could interpret what's happening with the original accumulation function at those same spots or in those areas, because to talk about what a change is doing, I'm saying near because I have to change a little bit. I can't be at a spot. I'm going to be in an area in a small neighborhood around x equals 7. As I go from left to right, the function would be going uphill, increasing, or downhill, decreasing around x equals 3. So same thing, if I said f prime of something like 1 is 0, well, then what I know from that on its own is that f near x equals 1 is, well, approximately constant. It's not increasing, it's not decreasing, it's fairly flat. Now, sometimes this, the increasing rarely happens for just an instant, just a very small moment that it's increasing. Usually happens for a while. There's usually whole intervals of increase and decrease. These rates of 0 sometimes occur just for a very small moment. So that's why sometimes you'll see something like near x equals 1, it's constant, or it changes very little is usually what's said, but there's lots of different things that could be going on. In this section, now let's see, I've got, this is not in between those. I know that by the time I'm at 3, my function is decreasing. So I'm drawing a function f here. Function's decreasing at 3, and it's increasing at 7. So someplace in between 3 and 7, there's got to be a spot where it turns around, and that would also have a value of 0. But at x equals 1, I don't really know what's happening. I just know it's generally going horizontal. And so if I were to try to connect the dots, maybe I'd say, oh, maybe f looks something like this. But I don't know what's going on over here. So I can't say that this is a maximum. I can't say that this is at a minimum. I don't know what it is. All I know is that it's a flat spot in the graph. So it could be flat. This left side could go down, or it could go up, right? So it could be a maximum based on knowing some of this to the right is decreasing. It could be not a maximum. It could be just a flat spot and that's it. So knowing that a derivative at a certain position equals 0 just on its own isn't enough to determine what's going on. It doesn't have to be a maximum or minimum. What we do know for sure is just like we know for these, based on the value being positive, I know something's increasing, negative means it's decreasing, zero means it's neither of those. It's constant. And that's what we know. So we use this setting the derivative equal to zero to locate potential maxes and mins, but a derivative equal to zero doesn't guarantee those. It just guarantees that we've got a flat spot, is all it does. All right, so let's get back to new stuff. Well, not new stuff, just kind of summarizing. So let me share a keynote with you, if I can get it to pop up. Hold on. Let me try this again. It's not showing in my list. There we go. All right, so we've talked about this before the test also. None of this is really new. This is just kind of extensions, extra practice, etc. So this is what we were just talking about earlier, test review stuff. Like I said, this isn't really new, but just to kind of repeat this is very important, and fundamental theorem of calculus. This is calculus. This idea is fundamental to our entire course. It's what all of this work you've done this semester is about. So this accumulation between two positions we can find from a rate function, adding up all the small changes one at a time, although we just express it this way since there's infinitely many, or by having an accumulation function and just comparing y final minus y initial. So in general, that was a numerical result. This is the more general form. If I start accumulation at some position A and go through a general X, then I can model a function f of x with this relationship here. So this A at the bottom, this is just a starting point. It can be any point, but the net accumulation begins at 0 then. The f of x minus f of a will be 0 if x equals a, which should make sense because those should be the same thing. But as we go on, the value of this expression grows or shrinks in the same way that this one does. This value on its own isn't known from this expression, just the difference between them. All right, so I think we talked about this one a couple times earlier this semester after the initial getting approximate rates. And I know we did this prior to the test, so I just didn't take this out, but we could write an open form expression for the exact change in height. Oh yeah, I remember that bar wouldn't go away last time. So the exact change in height between 2 and 5 seconds just by integrating r sub h of t between 2 and 5. And then we talked about how we could write the accumulation, or how we could write the closed form of this by finding what's called an antiderivative, undoing a derivative. So if this is the derivative of something, it'd be a derivative with t to the 2.3 power in it. As for this question 3, I believe this is kind of where we left off. And so it asks to write a function, open and closed forms both. If this will ever go away. For the height of the rocket, assuming it was launched from a 6.5 meter high platform. So if I want to know the height, not just the change in the height, I need to use this 6.5, meaning if I want to know my height, I'm going to start at 6.5 and then accumulate afterward due to this rate. So that's starting at time 0 up through any time t. If I'm going to call this h of t, this needs to be a t here. And then I'll use something other than t in my integral expression. So I'd integrate, I'll call it w to the 1.3 power dw. So this is my mdx expression that I'm going to integrate from 0 up through a general t, and then add on 6.5 so that we have that actual height, not just the change in height past time 0. This on its own is going to be 6.5 less than this, maybe obviously, but this just tells me how much my height has changed. This tells me what my height above the ground actually is. So if I wanted to write this in closed form, that just means, well, like find this without writing this expression, or do that f of b minus f of a sort of thing. So find f, which would be that, well, w to the 2.3 power, right, 1 power higher, and like we talked about before, compensate for power rules, bring down the exponent by doing this. So this is something that's an antiderivative of w to the 1.3. If I use power rule on this, I get exactly w to the 1.3 power. So this expression, I'm going to evaluate at t and at 0 and subtract. And notation for that, just by the way, and I might have shown you this before, maybe not. I think we did it before. Or not t. W equals t to w equals 0. When there's multiple variables involved, lots of times it's specified here. This line to the right we've done this a lot with like dy dx notation, and just line at the right at x equals 7. Tells you where to evaluate. When you've got one at the top and one at the bottom, that tells you do both and subtract, top one minus the bottom one. Now, that's just this integral part. And then I've got 6.5. So to finish this up, I'm not going to grab a calculator. I'm just going to write it in an expression. But I'd have 6.5 plus 1 over 2.3, which you could factor that out if you wanted, t to the 2.3 power, 2.3 power, minus, no, yeah, sorry, am I putting these in the wrong spots? And then letting w equals 0. It's going to be w, or 0 to the 2.3 power, which is 0. So this is my whole expression. This is a plus, not a t. So 6.5 plus 1 over 2.3 times t to the 2.3 power. There's a minus 0 in there, but you don't have to write it. I just wrote it for clarity. That's the value of this at the beginning. That's the f of a of f of b minus f of a. So in any case, this is a closed form function for height. It's not nice numbers, like decimals inside of fractions isn't great. It's not pretty, but this is closed form. It's just multiplication and addition and exponents. So in any case, that would express the overall height exactly of the rocket-powered basketball at any point in time. All right, so let me clear this off and let's go on. So keep in mind, and let me move something out of the way for me, accumulation functions, like what we just did, all you have to do is come up with something that has the derivative that you're looking at, and any of them will work just as well as one another. Because of the whole idea that constants have a derivative of 0, it disappears and you're not going to know about that. You're not going to ever see those initial constant values by looking at the rate. Just kind of like if I say write an equation of a linear function with slope 4, you don't know which one I have in mind. There's infinitely many. These all have the same rate of change because these constants all drop off when we take derivatives. So find the antiderivative or find this one particular integral. That's not really a question that we can ask. Generally, there's a more specific question to answer, like the initial height was 6.5. In a realistic problem, we have more information. But just to express generally the idea that if I have a rate of 3x squared, like this, r sub g of x, or whatever it might be called, if the rate function's closed form is something like 3x squared, then I know that the function is going to be of a certain type. In fact, I know that it's going to be x cubed. It could be plus or minus any constant imaginable, but that's the only differences that it could have. It can't have any other things multiplied onto it or divided by them. No sine functions thrown on. The only things that could be tagged on are things that are constants, so that in the derivative, it doesn't affect it. So this is this notation here, this is just a notational thing. This isn't a whole different sort of problem. It's just a notation to express, like, instead of writing out in a sentence all the time, what's the general form of the antiderivative for something like 3x squared? Notice it doesn't even have a name. There's no from a to b or a to x or anything. It's just a generic sort of, oh, if this is some sort of rate, what is its antiderivative like? We say this is a typical response to that, x cubed plus c. This c is called a constant of integration. It's not something highly meaningful. It just tells us that there's a family of functions that just graphically differ by shifting vertically, or algebraically, they just differ by a constant. They would all have the same rate function. But so these sorts of things, these are what are called indefinite integrals. It's kind of like part of a question. It's just asking what sort of thing has a rate like this? And we say, oh, the sorts of things are all x cubed plus something. So it's kind of to understand a general pattern or to express what the pattern is. So these are just kind of generic questions. So take a look at a few here. The first one, I'm sure you know what the answer to that is already, as we just talked about it. The second one also, but third, fourth, and fifth here, see if you can express the general antiderivative of each of these. So as a hint, they're all going to end with a plus c. But the most important part is the other part. So think about what sort of thing would I take a derivative of to have the derivative end up looking like this. So there's no evaluating, it's just no changing variables. Just figuring out what is the undoing the derivative part of this question. So for the next one here, this is also a power function. Power functions come from other power functions for the most part. There's one exception, we'll talk about that in a minute. But if I took a derivative of something and ended up with a 9th power, the original must have had a 10th power. This 5, I can deal with that at the beginning or deal with it later. But thinking about what we did here, this 1.3 power, finding an antiderivative would be like adding 1 to the power. And this coefficient came in to compensate for how power rule works. This is the reciprocal of that exponent, so that when I do power rule, they cancel one another out. The exponent becomes 1 lower, and this weird coefficient is gone. So in this case, because there was already a coefficient there, you could pretty it up a little bit and say, all right, so this is 1/2 w to the 10th plus c. And you see that, oh yeah, if I take a derivative of that, I get 10 times 1/2, 5 w to the 9th. So the way to check that you're doing antiderivatives properly is by, when you're done, take the derivative of what you got. This is a constant, so its derivative is 0. So, and that's going to happen every time. But the rest of it, check and see what you've got. Like this one. Well, maybe doing what we did last time. I'll worry about this -2/3 in a little bit, because coefficients, constant multiples, just kind of carry through, but sometimes they can be combined. So I'm doing an antiderivative. I want to know what has a derivative that involves m to the 11th power. Well, it must have been something with m to the 12th power. And to not mess up the coefficient, I'm going to do this. Again, reciprocal of the exponent. 1/12 m to the 12th. This part would have a derivative of m to the 11th. Tag that on. And just to clean up this, instead of writing a function that has 2 coefficients, what is that? -1/18 in reduced form, m to the 12th. And again, if you check, say, oh yeah, take the derivative of this, I get 12 times -1/18, -2/3, and m to 1 lower a power. So in order to do this, you have to be very familiar with derivatives. This is kind of the equivalent of, I don't know if you have like long division. It's when you learned about it, you had to learn your multiplication first because you do multiplication as a part of the long division process. Same thing here, we're kind of like working backwards to reverse this idea, just kind of undoing all of the things that we did to take derivatives. So there's one, before we talk about this last question, there's one other thing I want to mention besides just in general power rule stuff. But imagine that I had, let's see, 4 over x, otherwise known as 4 times x to the negative 1, or 4 times 1 over x. That 4 is just a constant multiple onto a power of x. Think about what would I have to take a derivative of to end up with something like one of these. And it's not a power function. This is the only power expression whose antiderivative is not a power function. So if you think of trying to do what we did before, increase the exponent and then multiply by the reciprocal, you'd likely see the problem. If I increase this, it'd be 0, and then the reciprocal of 0 does not exist, and we've run into a problem. But think about what sort of thing has derivatives that are like over x. That's a logarithm function. Natural log of x derivative is 1 over x. So multiply it by 4. Now it's 4 over x. Now, there's one other thing related to log functions. This is kind of a tedious domain issue, but this is talking about a general antiderivative. It doesn't tell us what values of x we're talking about. Natural log functions are only defined for positive values of x. So typically when people have these generic integrals, these indefinite integrals, and it involves natural logs, typically what people will write as antiderivatives involves absolute value signs to make sure that we're not using negative x's in a log expression. So if you do look this up, if you look this up on the internet anywhere, it'll say something with absolute values. Like, where on earth did the absolute values come from? Well, it's just due to the vagueness of indefinite integrals. It's just a thing added in to make sure that we're not talking about the wrong sorts of x values to have a value otherwise. So either of these is typically fine. And in an application, if you're dealing with something like this, it would be pretty obvious what your issue was. If you're suddenly using negative values, like, oh, this doesn't even make any sense. If, I can have this as a rate with negative values of x. But in order to express the natural log, I take absolute values of that. So in an application, it's less weird to just suddenly take absolute values. But in any case, I don't want to get hung up on that. But what I did want to point out in general, power rule wise, if I'm trying to integrate an indefinite integral of x to the something sort of power, well, this can equal one of two things. One of them is it can be natural log of x if n is -1. So if this is x to the -1, I write this. If it's not a -1 power, if it's anything other than -1 power, whether it's a whole number, a decimal, whether it's a fraction power, whatever it might be, any case other than the -1 power, add 1 to the power. So in general, then that'd be n plus 1, and multiply by the reciprocal of that power so that power rule for derivatives works out properly, and we're done. So this is if n is not -1. So just general antiderivative rule, although, once you've done this a few times, it's just working through like how to make power rule for derivatives work out right. But take a look at this last question here. This one is not a power function. Notice it's an exponential function. The exponent b is in the exponent, or the variable b is in the exponent. And whenever you encounter something, you say, well, let's see, do I remember getting things like this as a result of a derivative? E to a power in a derivative, yep, came from e to a power in the original, right? And e to the x was its own derivative. E to the something else is usually close to its own derivative. But for instance, if I were asking you, not find an antiderivative, but if I were asking you to take a derivative of this, it'd just be 5 e to the 4b and then chain rule times 4. So the difference between this and its derivative is just a factor of 4. So think about going backwards. This must be also fairly similar to its own derivative. But if I want to take a derivative of this and have it end up look like that, if I took a derivative of this, it'd be a times 4. This doesn't have a times 4, so compensate for it. Now that 4 would be canceled out, just like it was in power rule with these exponents. Instead of multiplying by the coefficient, we're like multiplying by the reciprocal in these power rule sorts of problems. Instead of multiplying on a 4 for chain rule, we're dividing by a 4 for chain rule. We're multiplying by the reciprocal. So this simple chain rule works pretty easily backward. We're going to talk about some more complex instances of reversing chain rule, like where it's not just a constant, but it's a whole other function level, like a composition of functions that's like a sine of a logarithm function, or something like that. We'll talk about that next class. But just as if it's just a simple times a number, when you're working backward, you can just divide by it. And that works with any sort of functions chain rule. So let's see, let me clear off this. And let's talk about some more things. So thinking about fundamental theorem of calculus, the meanings of these integral expressions. So we're moving away from what we were just talking about, some generic, what are called indefinite integrals, where you're just focusing on undoing the derivative process and not really solving any problem. These are full expressions. So I've got something, here's a rate function, and I'm measuring accumulation from 4 to 7, adding all of that accumulation up, and then taking a derivative. Well, if you think about what happens there, now I have no idea. This is a messy composition of functions. I have no idea what function might have precisely this as a rate function. But if you think about the meaning of this, let me just do this symbolically. So here I have something, let me call it r sub f. And apparently it's got a variable of x, so I'll call it r sub f of x dx. If I think about this rate function accumulating from 4 to 7, according to the fundamental theorem of calculus, this part of it should be f of 7 minus f of 4, right? The function whose derivative we see, whose rate we see, we want to know the change in it between 7 and 4. This is according to our fundamental theorem of calculus. So this expression looks awful, but maybe you can see that if I take a derivative of that, f of 7 is a number. I don't know what number it is, but it's a number. F of 4 is a number. These are both constants. This isn't a function, this is a value, and that's a value. If I take a derivative of a number, I get 0. So despite the fact that this looks awful, and I would have no idea how to do just this portion of it, and I'm not just saying that like you don't know yet, like literally me, I don't know how to do this. Maybe I could work on it for a while and figure it out. But this expression, its value is 0 because it's asking us to take the derivative of something that's a number. And the derivative of a number, a numerical value, is 0. This isn't changing. this rate changes from 4 to 7, but by the time I've integrated order of operations here, do this part first, we get a number. Take the derivative of a number, and it's 0. So daunting expression, but if you know how the fundamental theorem of calculus works, realize that this just has a value of 0. Now, is this a useful skill? Knowing that an expression like this is equal to 0, maybe not, but let's extend it to something where it's not quite 0, but we can use some of the same skills of not actually finding antiderivatives, but just being able to re-express things and then take their derivatives anyway. Because maybe you can see this involves finding an antiderivative and then taking a derivative. So to some extent, those two cancel out. But just kind of like if you have squaring and square roots, you have to make sure that the domain is right, so you know whether you're going to write a positive number or a negative number or something like that. This is a integrating, but only over a certain section, and then taking a derivative, or finding an antiderivative change and then taking a derivative of that. So something like this, it's not a whole lot different from the question before, but one change here means that this is going to come out a little bit different because this is an x, not a 7. So in the previous question, this integral portion had a numerical value. This time it doesn't, but I bet we can do it anyway. Think about the same things. So just using the same notation, let me just give a name to this. So, because I don't know how to find an antiderivative for this, but if I call this r sub f of t this time, then I can call its antiderivative, any antiderivative is fine, so I'll just call it f. So an antiderivative of f evaluated at x and evaluated at 4. And then we take a derivative with respect to x. So that's not too bad. Last time was f of 7 minus f of 4, which was all numbers and it disappears. This is a number, so this derivative is going to be 0. What's the derivative of f of x? I don't even know what f of x is, but I know what its derivative is. It's that with an x in that spot. This is the rate function, the rate of change of function f with respect to t. I subbed in x and 4 and subtracted. Now I need the rate of change of f with respect to x. Well, that's just a change of variables. This would be r sub f of x minus 0. The derivative of f of 4 is 0. And r sub f of x is, what do we have? Sine of 3 cosine of x. And that's the end of the question. So you can maybe see here, so we had a net accumulation between 4 and x, and I want to know the rate of change for that. Oh, well, it's just this rate function that we had before, just the letters changed is all, and that's because of this letter change here. So rate of change, net accumulation, back to rate of change. And so the fact that this f of 4 was here didn't really matter. This could have been a 0 or a 17 or anything, any number here, and this would have worked out exactly the same. If this is anything other than x here, and this was still dx, if these two weren't the same letter, then this wouldn't work out the same, exactly the same as this. But here, let me show you one more like this. Oops. This is the challenging level. In the very last homework assignment that's due, I believe, homework, what is it, 21 or 22, whatever the last one is, that's due on Friday of this week, you'll see a couple of questions that are similar to this in amongst there. I'm leaving this all here for right now just for comparison purposes. But take a look at this last one. And again, it's a different rate function than was used on the previous two, but that's not really the important part. The important part is it's kind of a strange expression on the integral sign for the end of the accumulation. So think about how you could write this out symbolically so that we can think about how to evaluate without actually needing to know what is the antiderivative of this, what function has a derivative of this. We don't actually need to know that in order to answer this question. Because if we figure that function out, we'd be taking a derivative of it anyway, so it should be something similar to this original, although it's not going to be quite as simple as the last one, just switch a t for an x and we're done. Let me change colors here. So let me call this, oh, sorry about that. This is not letting me click on things properly. That's 1, 2, there we go. All right, apologies. So here is, I'll call it R sub f of w, rate of change with respect to w, or rate of change of f with respect to w, based on the fact that there's w's in here. But I want to know what the net change is between input values, independent values of -5 and e to the 4x. Well, that's kind of a strange one. But if we just do kind of what we did before, say, all right, so f is the accumulation function. I want to know the net change between f of e to the 4x and f of -5. And that would be equivalent, this expression here, for some unknown function f, as of yet, is the equivalent to this integral here. And then we want to take a derivative of this. So just like before, derivative of something that's a number, that's 0. Derivative of f of e to the 4x. Now the derivative of f of x would be r sub f of x, or something like this. But what I want is a derivative that involves, if you can see this maybe, it's a composition of functions here. So if I knew what function f was, let's say f of x was sine of 2 plus x, just to make something simpler to write down. If I said f of e to the 4x, it would be sine of 2 plus e to the 4x, right? If I take the derivative of this, it's just, f prime of x would just be something with a cosine. And then the derivative of the inside is just 1. Cosine of 2 plus x, done. If I took the derivative of this guy, it involves chain rule. Like this one is simple chain rule. Derivative of this is just 1 though, so we don't see it. The derivative of this guy here, derivative of f of e to the 4x would involve cosine of this 2 plus e to the 4x. So cosine with the inner part intact times the derivative of this inside part, which isn't just a 1, would be 4e to the 4x. So down here, taking a derivative of, or just kind of in general, derivative of f of g of x. Think about how chain rule works, generally speaking. Oh, well, to find the derivative of f of g of x, I take the derivative of the outside function, leaving the inner part intact, and also take the derivative of the inner function with respect to x. Here are g of x is just e to the 4x. So if I want to take this derivative, I do f prime with e to the 4x inside, and then take the derivative of e to the 4x. And then this part here is minus 0, as we said. So let's just think about what this is then. F prime, that's just the same different notation for r sub f of e to the 4x. So going back to our other notation, I'm going to move up a little so I don't run out of room. So this is r sub f, not of x, but of e to the 4x times 4e to the 4x. I'll simplify off the minus 0 already. But if I want to write this out, oh, r sub f of e to the 4x, this is r sub f of w. R sub f of e to the 4x is going to be 1 plus e to the 4x squared underneath. So this is not an easy problem anymore, but it's just like level 1, level 2, level 3. So this one's, once you realize what's going on, this one's easy because this is a derivative of a constant. In this case, we're taking a derivative of essentially just one of our infinitely many possible net accumulation functions. This one's a net accumulation that starts at 4. But the rate of change of a net accumulation function should be the rate of change of any, they're all the same. It's all the same rate, which is this. This actually involves making a composition of functions because of this endpoint not just being a value of our independent variable, but a function of our independent variable. So I'm going to pose a couple more questions for you that are of like these harder varieties here, but you're going to see some of those in the iMath AS assignments as well. Let me clear this off and let me click. So before next class, what I'd like you to do is see what you can do with these 3. So the first 2 are maybe not too challenging. The first one looks kind of like that level 2 question from the previous page. This one looks a little different. Mystery starting point instead of mystery ending point. Shouldn't make it too much more challenging than the one above, but a little bit different. And then here's another example of that hardest sort that we just did. But again, all of this is just a way to integrate all the different pieces. I didn't want to make this a pun, but no pun intended. We're integrating all the different uses of the fundamental theorem of calculus into one sort of problem, like all the different understandings of rate and accumulation and rate of change of accumulation and rate of change of accumulations of rates of change. So to some extent, we get back to where we started because we're taking derivatives of antiderivatives, but with slight variations made, we can express slightly different things. So I'm going to stop at that for today. I think that's enough mind bending for one day. But before Thursday, take a look at what we're going to be doing. I posted kind of an outline of the lesson for today and Thursday at the same time yesterday afternoon. And you'll see some of the slides. I know sometimes they're not completely visible because there's things that pop on and off of the screen, but just some of it you can see and kind of have an idea where we're going. But on Thursday, we're going to talk a little bit about the final exam, wrap up one more different way to apply the fundamental theorem of calculus and understand net accumulation visually, and then just kind of wrap up the semester kind of debriefing of what we did so that you can like focus on the overall goals as we go towards studying. So I'm going to be around for another hour or so for office hours. If you want to stick around and ask questions, please do. You unmute yourself. I'm going to take this off of that screen though. So if you have any questions, chat or ask whatever you've got. Thank you so much.